is a waveform and how are they used in the industrial inkjet process? Here's a diagram of what's going on inside the printhead. The waveform is an electrical signal that's sent to each of the nozzles inside the printhead. The nozzles are made out of a material that moves when an electrical signal is applied. As you can see, when voltage is applied, in this particular case, the back of the nozzle is moving. When the nozzle expands, it draws ink in, and when the nozzle contracts, it jets out a drop. And this process is repeating thousands of times per second to form the jetting that we know inside the process. So we're going to focus on the electrical signal in this course today. Depending on the design of the printhead and which manufacturer it comes from, the waveform can take a couple of different shapes. So there are some versions of the waveform where it is an active high, so voltage is applied in the positive direction, which causes the nozzle to move. There are also versions of waveforms where the printhead sits idle at a voltage and a drop in voltage is what's causing the walls of the nozzle to move. And then there are some printheads that are a little bit of both, where they can move in the negative or the positive direction. Regardless of which printhead you're using, they all follow the same fundamental waveform optimization techniques, and those are what we're going to cover today. Before we get into the details, a good thing to understand is, why do we care? Why does this really matter, and what is this going to do for us as inkjet developers? So the printhead manufacturer often recommends a waveform for their head that performs well under most circumstances. And that's a great place to start if you're just looking to jet and see how your ink performs or see what the process looks like. If you've got an abnormal ink, you might find that the recommended waveform really doesn't perform well and you've got to explore changing it. Or if you've got an application that's really demanding, you've got to optimize every aspect of the system, and maybe jetting well isn't good enough, and you've got to jet perfectly. And that's where looking into making improvements to the waveform could help. Some of the improvements that people are most often looking to make through waveform changes are changing the drop volume, increasing the speed of the drops, reducing any satellite formation, or improving the overall stability of the jetting. And these are all things that can be accomplished through optimizing the waveform. The basic parameters that we're working with for a given waveform is the voltage or the amplitude of each individual pulse, how long that voltage is applied for, which is known as either the pulse width or the hold time, depending on the manufacturer. And if you're doing grayscale printing, where there's multiple pulses involved, the spacing between those pulses is another factor. And we'll go through how to make changes to all three of these and what's the process you can follow. To start with, it's important to kind of define what the goal is of your jetting. Every application is a little bit different. To kind of demonstrate this, we can ask ourselves, we'll take a look at two waveforms and we'll try to figure out which waveform is better. One waveform, waveform A, we can see does not have any satellite formation at all throughout the entire drop formation, whereas waveform B does have some satellites. So depending on our application, waveform A or waveform B might be better. And some applications would tend to go towards A and some would go towards B. Here's why. If we take a look at what the actual printing looks like for those two waveforms, we can see that waveform A is a little bit less consistent. So the edges are a little bit more ragged, whereas B, the lines are a bit more well-defined. The thing about A versus B, and we'll go back to these waveforms, is not only does the satellites matter, but the speed of the drop also matters. In some applications, having a higher speed is better, and you can actually sacrifice some of the satellites, and more satellites are acceptable. An example like this would be textiles, where you're trying to throw the droplets of ink a really far distance because the print heads tend to have a pretty large standoff. So in an application like that, high velocity of drops trumps perfect drop formation without any satellites. Something like printed electronics would be the inverse. The print heads can normally be very, very close, so the velocity is not as important as making sure there are no extra drops of conductive material traveling anywhere else that they're not supposed to be. So we were talking about where do we get started. We want to define our goal. And our goal for our waveform kind of breaks down to these 5 criteria. So how many satellites are acceptable for our particular application, both in terms of the number of the satellites and then also the size of the satellites. The volume of the drop, the velocity of the drop. Again, each application kind of has an acceptable range of throw distances, and so we need to establish how far from the print head do these drops matter. And then the speed / frequency / resolution. All 3 of these things are tied together. But this is the speed of your printing process. So how fast is your printer need to operate to be able to do your application well? So all of these things are things that we're going to take into consideration for how to optimize a waveform to kind of set our goal. And it's okay if in the beginning you actually don't know the answer to all of these things. Most often you won't, and you'll have to do some printing before you can really decide how to balance all of these things. So what we did for our particular setup is we have a drop watcher and a sample printer. So we took a look at the jetting on the drop watcher side, and then we took a look at the resulting sample print. And what we can do is we can see the drop watching and the resulting print, and it really ties together criteria like how does the velocity impact the print? How do the number of satellites impact the print? So that's the system that we used here throughout much of this process. To get started, we're going to use the printhead manufacturer's recommended single pulse waveform. Most printhead manufacturers kind of define this in the user manual for the head. They outline how to make something like this and what it looks like. In the case that the printhead manufacturer doesn't show it in the user manual, quite often you'll be able to either from your printer provider or the printhead manufacturer themselves, they'll be able to just send you a waveform, and you can use that to get started. So what we'll do is we're just going to scale the voltage of that waveform up and down to experiment with different balances of drop speed and the number of satellites. So the higher the amplitude of the waveform, the higher the speed of the drops will be. And it quite often tends to be the higher the number of satellites. Most printheads allow you to simply scale a waveform without making any other modifications to it. So we'll just scale a default waveform through a bunch of different voltages and just take a look and see what happens. So here's an example of an image where each different slice of the image uses a different voltage scaling. So the lowest voltage is over on the left, the highest voltage is over on the right. So we test a bunch of different waveforms with different voltages and take a look at the jetting. This was captured on a Ricoh Gen 5 printhead, and it uses GIS drive electronics. One thing that's nice about the GIS drivers is that they allow you to send commands to the drive electronics through software to change parameters of the waveform. So for example, we can create a list of voltages that we want to test, and automatically send them to the GIS drive electronics, and it's going to change the waveform automatically. So creating an image like this only takes a couple of seconds because we've got the software all tied together between the drive electronics and the drop watcher to change the waveform, capture an image, make a change to the waveform for the next voltage, capture another image, and put all those together. So we use that functionality within GIS a couple of times throughout this course, but that's just to give you a little background on how we're generating this image. So what we can see is that as the voltage increases, so does the speed of the drop. Each of these slices is taken at the same moment in time. So we can see on the slower end of the voltage, we've got our distance from the print head on the left here. The drop hasn't even traveled 0.5 millimeter, whereas at the same moment in time on the higher voltage, the drop is almost 1 millimeter from the head. So the drop velocity is definitely increasing as we increase that voltage. You can also clearly see that the number of satellites is increasing. And again, based on the application, one of these is going to be better than the other. And we have to decide where's the right balance between the two of those. And the way that we're going to do that is by actually printing our images. So we see what the drops look like here. We're going to take kind of a representative sampling. So maybe this waveform, and this waveform. And we're going to actually print a sample image and we'll compare. So we're looking at things like how straight are the lines, like we were before. Looking at things like, is the ink bleeding? And then also looking at things like, is there any satellites that are present, or how does the shape of the drops compare? And depending on the distance from the print head to the substrate, how fast your substrate's moving, all these different things that are somewhat unique to your application, those are going to help decide what's the right balance between speed and clean drop formation. So we'll take this test and kind of put it in the back of our minds of, what are we looking for here? Is a higher speed more acceptable, or higher satellite count, or do we need to be slower with fewer satellites? To get started with the actual optimization, we're going to bring that voltage back down to the point where we get a controlled jetting of a nice looking drop with limited satellites. Usually with just about any waveform in ink, you can lower the voltage enough to get to this level. So with the print head here, this is a Dymatics Samba drop that we're using from here on out. So we've lowered the voltage to the point where we've got no satellites. So this is a double pulse, again, for measuring the velocity. So there's actually no satellites here. And we've got a velocity of about 5 meters per second. So for some applications, this velocity might be a little bit slow, but again, this is just going to be our starting point for the optimization. The next step is we are going to sweep through different values of the pulse width. So again, the pulse width is how long we are applying a voltage for. And we're going to find which value of that pulse width yields the maximum drop volume and velocity. In general, the pulse width tends to be quadratically related to those velocity and volumes. So there is going to be an optimum pulse width that we can find based on this test. To kind of explain why that is, I put together a diagram here. So each of these slices is the nozzle, and we're just looking at what's happening to the nozzle over time. So when the voltage is applied, the nozzle, the back wall of the nozzle chamber moves. And that creates a pressure, right? So as we're applying voltage, the wall moves more and more and more. And then when we back that voltage off, the wall goes back to the way it was originally. It's